Today we're going to be exploring solids. We're going to identify the solids and the parts of the solids. A solid is a different way to say a three-dimensional figure. Today's three-dimensional figures will be titled a polyhedron. So singularly it's polyhedron, and as a plural more than one is polyhedra. A polyhedron has to be closed. Just like when we talked about polygons earlier, they have to be closed. There can't be an opening. And the reason it's called a polyhedron is because it is made up of polygons. So remember from our previous lessons that polygons cannot have curved edges. The parts of a polyhedron are the face, edge, and vertex. The face are the plane shapes. What I mean by that is any flat surface is going to be your face. In the case of a polyhedron, your flat surface must be a polygon. So the polygons themselves are the faces. When we look at our picture, our top and our bottom are kind of the same matching rectangle. The front here and the back are the same matching rectangle, and then the left and the right are the same matching square. Where two of the faces come together, such as the square here and the rectangle in the back, there is an edge. An edge is just a segment where two faces come together, or two polygons come together. And then last but not least is the vertex. Just like everything else we've done this year, a vertex is a point, but this time we're going to have three edges come together, or three segments come together to make that vertex. You can see we have a couple of lists here. The first list I'm going to title polyhedra, because polyhedra is plural for polyhedron, so we have three polyhedra. And the second list is not polyhedra. This second list, or second grouping of pictures, well, I have just messed that up altogether. Polyhedra, sorry about that. So these are not polyhedra because of the curve. So you can see there are circles here, there's a curved edge here. So the first list is polyhedra, we're all polygons, and then the second listing is not polyhedra because we have circles and curves. In the realm of polyhedra, there are two types of polyhedra we're going to talk about. One is a prism and one is a pyramid. A prism, like a tissue box, is going to have two identical bases. Those bases have to be made up of the same polygon. Not only do they have to be the same, but they have to run parallel to each other. If they're not going to run parallel to each other, we really aren't making a prism. So what happens with the other faces? The other faces have to be rectangles. So the question becomes, well, aren't they all rectangles? And the answer is no. Yes, a tissue box is all made of rectangles, so it would be a rectangular prism because it's all rectangles. But what if the bases are a pentagon and everything else is a rectangle? Then we would call that a pentagonal prism. So you could have triangles with rectangles, you could have octagons with rectangles, you could have hexagons with rectangles. That's still going to be a prism. A pyramid, like the pyramids in Egypt, are going to come to a single point because they have one base and the remaining faces are triangles. So these are now triangles. Just like a prism, a pyramid is going to get its name by the shape of the base. So if the base is a square, then it's a square pyramid. So in Egypt, we see square pyramids. There are triangular pyramids, there are hexagonal pyramids. Again, it is determined by the shape of the base. So if we go back up here at the top, in our polyhedra list, you can see that this has a hexagon with triangles and it comes to a single point, so this is a pyramid. Neither one of these come to a single point. There are points, but not a single point like a pyramid does. This is all rectangles, but it is still a prism. This one's a rectangular prism, like our tissue box. Our situation here is we have a triangle in the front and we have a triangle in the back, and then we have 3 rectangles. So this one too is a prism. This is an example of a triangular prism because we have triangular bases. You'll notice that base does not necessarily mean bottom. Base, again, are the 2 identical parallel polygons. Over here, these were not polyhedra. Doesn't mean they're not 3-dimensional figures. It does not mean they're not solids. It just means they have a different name and they don't fit under this category. So our first one here is a cylinder. Our second one is a cone, and we're going to learn about those later on in the chapter. So let's look down here at our examples. It says determine whether the solid is a polyhedron. If it is a polyhedron, name it. If it is not, then explain your reasoning. So first one out, number 1 here, we have a base that is a circle, and so this would not be a polyhedron because the base is a circle. On number 2, you can see we have a trapezoid here, and so on the back side we have a matching trapezoid. Now this doesn't quite look like a rectangle, but I promise you it is, so the rest of them are rectangles. So yes, this is a polyhedron, it's a prism, and since this was a trapezoid, this is a trapezoidal prism. So you kind of just write the word trapezoid and then put AL at the end, so trapezoidal prism. Number 3 comes to a single point made up of a bunch of triangles, and they're all polygons, so yes, it's a polyhedron. It's a pyramid, so we're going to look at the shape of the base, and the base is a hexagon. So this is a hexagonal pyramid. So one more time, let's look up here. Here's our same hexagonal pyramid. We have a hexagon as the bottom. It's a pyramid. These 2 faces were triangles, so this is a triangular prism. And this is all rectangles, so it's a rectangular prism. So now we're going to move on to the next topic, and I'm going to get it into the spot that matches the recording area. Sorry about that. So we're going to look at concave versus convex. So in a polygon, we have concave and convex. Pretty much the same criteria are going to apply to a polyhedron. We have first off the convex, which is where all the faces are convex, all faces convex. So all the prisms and pyramids you've seen at this point have been convex. There are special kinds, they're called regular polyhedron, and that's when all the faces are the same regular polygon. So if you have all squares, you have a cube. If you have all equilateral triangles, I'm not very good at drawing this one, but we'll give it a shot. So here's the 2 equilateral triangles, and then we kind of need to make it 3-dimensional like that. And that would, it has its own name as well. Most people call it a diamond. I know there's a floating diamond in one of the video games, so you might want to think about that. Our second kind is concave. It's also known as non-convex. The first type, all the faces are still convex, which is kind of confusing that all the faces are still convex, yet it's called concave. It's concave because if I try to connect these 2 vertices, you'll see there's a divot in there. So there is no proper term for this type of polyhedron. I call it warty. I don't really have a better name for it, so I call it warty. Again, all the faces are convex, but they're put together in such a manner that there is a divot, and therefore it's concave. The polyhedron is concave. The second type of concave polyhedron is one where at least one of the faces is concave. So it seems that if you have a concave polygon, you should have a concave polyhedron. And you do. In this situation, we have an octagon here that's concave, and its twin base back here in the back is also concave. So you can see that the polyhedron dips in. You can see that divot right there. Continuing with this same train of thought, we kind of look at our star here. The star is concave, so the polyhedron is concave. Number 2, all the faces on this prism are convex, and none of the vertices dip in or have a divot, so this one is convex. Not only are all the faces convex, but the polyhedron is convex. Whereas when we get to number 3, every face here is convex, and at that point we're like, okay, is it like number 2? Is it still convex? But remember, anytime all the faces are convex, you really get 2 choices. It could still be convex, or it could be concave. It could be this kind of warty one. So can I try to connect some vertices and get a divot? And the answer is yes, I do get the divot, so this is concave.